So our next speaker is our final speaker, but last is not least. Today, Ángel Verbel from the Universidad Nacional de Colombia will give us a talk about rare earth element minerals associated with the famous Colombian emeralds. Ángel did his master's and bachelor's at the National University of Colombia. And I don't know if he planned on me saying this, but he's actually one of the perfect candidates for an ODH early career day, because Ángel had planned to do a PhD after this, but due to the COVID restrictions and the necessity of the COVID travel restrictions and the necessity of starting a project, he was unable to commence his PhD project. And so now I know that Ore Deposits Hub talks are a small constellation prize, but at the very least, he gets to share with us some of the things he was working on before this pandemic has disrupted sort of his professional career. So I hope that's okay to say, Ángel, and yeah, the floor is yours.
Oh, thank you, Aaron, and thank you to you all guys for this invitation. Well, I'm gonna talk about the rare earth element minerals associated with emeralds, because usually we see that Colombian emeralds are always studied only the emeralds, and there have been reported since the early extraction of this mineral that they get really along with these rare earth element minerals, and where you can find parasites from the size of a soccer balloon, actually. So that's why I started this project with my master thesis. So we start with a little bit of the location. We are at the northern part of South America, in Colombia, where the Andes diverge into three mountain ranges: the Eastern Cordillera, where two emerald belts are found, the eastern and the western one. We are gonna focus on just in the western one, the Central Cordillera and the Western Cordillera of Colombia. We can see here a geological map where we can find some of the localities in the orange squares are the ones that we studied. And all these, as you can see, are restricted to these Cretaceous formations, the Muso and the Rosa Blanca formations from the lower Cretaceous series. So a little bit of the geological evolution. All of this started in the late Paleocene in the Devonian to the early Permian, where there was a continental collision, a possible continental collision, where the Paleo-Central Cordillera was formed, and a Bakar basin is start to form in here. So as the times go by, the Bakar basin evolve. We can see here this crosscut. This section is more or less at the level of the mineralization. So we can see a paleo elevation here, separating our basin into two sub-basins. So restricting the origin from the sediments to different places. These two basins get then into just one at the upper part of the early Cretaceous series, and they are at this place they are completely one. And in the late Cretaceous also is accreted the Western Cordillera. Then in the Paleocene, in the Middle Eocene, late Paleocene, the stress change, and the Cordillera start its uplifting to the configuration that we can see nowadays. So here we can see the formations where emeralds are restricted to. There are the Rosa Blanca formation and the Muso formation map. This section is in the area of interest. So we can see that they are constrained by this composition of calcareous shales and limestones, and with a less representation of the mineralization, but not least the Rosa Blanca formation that is mainly made for limestones. So in the mineralogy that we observe, we separated into three different stages. In order of its formation, we have a first stage that is formed parallel to the stratification, a second one that is discordant to the stratification, and the third one that is formed from breccias, that is the more important stage, because we here can find the emeralds and the rare earth element minerals exclusively. So in the first stage, we find the one of a really important thing, anthracite, that is formed by sulfide reduction from the organic matter of the shales. So this sulfide reduction forms the anthracite, and also gets able to be acidic, sulfuric and carbonic acid in the system that later on react with iron to form pyrite, and with calcium to form calcite. In here we can see that there are some fault planes along with the stratification that suggest that these spaces where these early stages are formed were formed during a compression stage where the stratification acts like a decollement plane, letting the mineralization get into this part. Then the stress exchanges forming these pull apart structures where they are oriented perpendicular to the main stress that would be with this orientation. This stage mineralogically is sort of similar to the first stage with a lot of calcite. We start lacking the anthracite, but we see more sulfide like pyrite and sphalerite. So here we can see the cross-current section in the microscope with some sphalerite, pyrite, white mica, pyrrolite, and calcite with these fibrous textures. The third stage is, well, the economic one is formed by these breccias that we can see in here. We have some polished sections that we made where we can see some of the earliest stage with some of the earliest pyrite that goes along with the stratification of this portion of the rock, some new pyrite forming. Calcite, we can see the emeralds forming, but there are more things happening in this stage. We can see that at the beginning of the stage, we have a lot of collision between all the parts of the stage. So we can see some of the minerals with these right angle fractures due to these collisions. Then we start seeing some corrosion, some chemical corrosion on some pyrite, given that now at this point there is no more like the collision that is predominant in this breccia state, but more a chemical one. Sorry. And at the last part of this stage, things get really quiet. So we can see really beautiful low temperature quartz that where you can see there are both termination of the pyramids that are usually frequent in high temperature quartz, but given the conditions at the last part of this stage, we can see a really beautiful development of this crystal. We can also see plagioclase, albeit in composition that is formed during this stage, but there are some samples where we can, this is based on a previous bachelor thesis that found plagioclase in this fragment from previous stages that have the rouge-thorn twinning that is typical from plagioclase from diagenesis. So we have two types of plagioclase in the system, but these ones are formed during the hydrothermal process. We can see also the emeralds forming a really beautiful form, so they have the time and the space to grow. We also find fluoride and some calcite. Also, the main part of this talk, we see the parasites, also with beautiful forms in here. These are really large crystals of parasites, so they are easily distinguishable from the calcite. But when you get to a different level, like when they are really small, you can not distinguish by typical optical techniques because the refraction index are really similar. So we start using our microprobe to see them in the back skeleton electron. And we also found not only the parasite, but also we found these brighter points in here that correspond to basnasite. And this one these ones there are chemically correspond mainly to calcium and cerium in composition. It's just like the leftovers from these processes at the last part of these stages. So we start doing some calculations. This is the one of the equations that for the processes that we found where parasites can is transformed to calcium, rare earth elements, carbonate ions, fluorine ions, and basnasite. So as we saw in the previous image, we saw the basnasite with the calcium and rare earth elements. So we calculate the delta of the get free energy for this and the other different reactions that take place into these systems using previous data from William Jones, Misigov, GC, and a lot of previous works. These are the get free energy for the elements and the calculation of the equilibrium constants for this reaction. This is made for all the reactions that we consider to be taking place in this deposit. So we construct this diagram with the logarithm of the activity of fluorine and the logarithm of activity of carbonate, and we measure our parasite fluorides and basnasite that we found, and we found that when fluorides are formed, they tend to have a higher activity of fluorine, decreasing when you start to forming parasites. And at the last part of the stages, we start forming the basnasite with our leftover of calcium and other rare earth elements. So we see that at least for the formation of these minerals, these are really important. But we wanted to compare with emeralds to see what's happening. So one of the things that we saw was the salinity in the system in different minerals. It is measured by many authors. So here we can see that quartz and calcite record salinities from around a little bit less than 25% of chlorine sodium and up to almost 45%. So because as I told you, these minerals are present almost in all of the stages of the mineralization. So they have the record of all the changes in the salinity in the system. Meanwhile, the fluorite, emeralds, and the albites measured are more constrained to be around 33% to 45% of chlorine of salt in their fluid inclusions. So at first glance, if we see this, the first things that we can think is that you start precipitating things with a higher content of salt, and then the fluids start to getting out of salt, and it would be decreasing. But as I already showed you, these minerals are formed in the last stages of the mineralization. So we were questioning what's happening here. So we put along a lot of statistic and correlation models of the variables to see what was the influence between variables. What variables were influenced the other ones. This, along with some base theorem, using the previous experiment by other authors that I already mentioned, we can calculate the ideal composition of the fluid that can produce the reaction that can react to form the association that we found in the system. So we have albite formed during the generic processes that we already saw. Rare earth element transported mainly as fluorine complexes. Beryllium transported also as fluorine complexes and also as chlorine complexes. Sulfuric acid, iron, calcium, and quartz from the main rock. This in an aqueous solution can form calcite, pyrite, fluorite, the parasites, basnasites, emeralds, plagioclase, albite, and we have leftover some salt, sodium, and some hydrogen atoms. This excess of salt is that we can see in the fluid inclusions of the emeralds, fluorides, and albites. Hence, we in these minerals, given this, we can see higher contents of salinity in its fluid inclusion than the previous generation of calcite and quartz. So using this equation, we could be able to estimate not only the possible emerald contents in these breccias using mass balances with unaltered rock and altered rocks. We also would be able to see if there is any potential for a light rare earth element deposit in the area, given that this seems to be very frequent, not only as a big crystals along with emerald, but also as as a smaller crystals, but with a wider spread in the system. So these anomalies of fluorine in this case causes left over at the end of the formation of the bastnasite can be used to trade as a metallogeny in exploration guide to find new deposits in the area of emeralds, and also to explore for rare earth element concentrations in the area. So thank you to you all, to our deposits, our panelists, and to everyone for being here listening.